Hello everyone. Today I will try to discuss few of the graphs that is needed in the practical examination, because nowadays this animal ethical committee, it has been very strict, and since last few years it's not possible to practically perform these experiment, and these graph, they are related to skeletal muscle graph as well as the cardiac one. Okay, so first we will start with the skeletal muscle graph, and in these graph, like, what is the significance of doing these graph? The significance of doing these graphs is like whatever we have read in the nerve muscle physiology, that we are performing experimentally, so that it will become easier for us to understand the thing as well as to memorize those things. Like whatever we have read, if we perform it practically, so it will become much more easier for us to imbibe it, right? So we will start with this, the simple muscle twitch graph. Like, you will get the graph in your practical examination, and the examiner will come and ask you to comment on the graph. So first you should learn how you are supposed to say the thing. Like, if the examiner comes and asks, like, okay, comment on the graph, so don't just rush into the thing, like to come to the conclusion. Say it. There is a manner, there is a method of saying the thing. Like, this is a simple muscle twitch graph, or you can say this is a simple muscle twitch graph which is plotted by using the nerve muscle preparation. Now, how this nerve muscle preparation is done, I'll just try to cover the basic thing. Okay, basic thing, because it's not practically possible to live demonstrate the thing. So in this one, the nerve muscle preparation, this is like we do the thing, like, say we will take the gastrocnemius muscle. Okay, the gastrocnemius muscle of a frog. So what we do for taking this graph, we do the dissection of the frog, and I will just come to the basic point. Like, we take the sciatic nerve, we dissect out the sciatic nerve starting from the its end point at the spinal cord. So we won't cut the entry point of the sciatic nerve in the spinal cord, right? We will just cut the spinal cord above and below where the sciatic nerve enters. So it will stay intact. This part where the sciatic nerve is entering, it will stay intact, and we will trace this sciatic nerve. It supplies the gastrocnemius muscle. So say this is the gastrocnemius muscle. Okay, gastrocnemius muscle. Okay, and so this nerve is entering inside this gastrocnemius muscle. So over here there is this knee joint. Okay, then this one we can call it the ankle joint. Okay, like in the frog. So we won't cut any connection between the vertebral column, this one spinal cord, sciatic nerve and gastrocnemius muscle. We will let it remain the intact. Okay, now while performing the experiment, all the experiment regarding the skeletal muscle, what we will do is we will stimulate the sciatic nerve at any point in between the this is the neuromuscular junction, right, where it enters, and this is its entry point at the vertebral end. So we can call it, this is vertebral end and this is muscular end. So at any point we will put the stimulus, and that stimulus will make the generation of action potential within the nerve, and that generated action potential will reach at the neuromuscular junction. There will be the release of neurotransmitter, and that neurotransmitter will act at the end plate, generate the end plate potential, ultimately it will convert or generate the action potential within the muscle, and then there will be the generation of contraction, right. So, that is the basic of doing all these experiment regarding the skeletal muscle. Okay. So, when we do this, or we can say we try to draw this simple muscle twitch, what we do, we take a drum, okay, that rotating drum will be there, okay, that rotating drum will be there, like say this is a particular rotating drum, okay, and we will take that now muscle preparation. As I told you, like there will be the vertebral column end, and this is now, this is muscle end, and this is the muscle. So, we will put it at the myograph board, okay, we will put it at the myograph board, and one part, this end of the muscle will be attached to the recording lever. There will be the recording lever over here, okay. So, whenever we stimulate this now, this muscle will contract. Because it is contracting, what it will do, the connection of this recording lever is such that when the muscle contracts, it moves upward, okay. So, if the drum, this kymograph drum, this is not rotating, then we will just get a straight line like this way. When the muscle contracts, this lever will move upward and we will get a straight line. But because we want to notice all these things, the latent period, the contraction period, and the relaxation period. So, what we do, we make this drum to rotate, this drum will rotate. There are different speeds. So, we will make it to rotate at the maximum speed, and that maximum speed is 640 millimeter per second. So, if this drum is rotating, then we won't get a straight line, because this lever is moving up when the muscle contracts, and it moves up, and then automatically it will come downward. When this drum is stationary, it will come downward on the same line, but this drum is rotating at the speed of 640 millimeter per second. So, obviously, we will get like this straight line and then the downward line. So, that is what type of the graph we get over here. Okay. So, in this one, if we look at this graph clearly, if we look at the graph, see, I will try to enhance it a bit. See, this is the baseline, okay, this is the baseline, and this is the point of the stimulus. This is the point of the stimulus. So, we have provided the electrical stimulus to the nerve, and now we before providing the stimulus, we have started the drum. Drum is rotating. As soon as we provide the stimulus, what will happen? Because we are providing the stimulus to the nerve. Okay, we are providing the stimulus to the nerve. Like say this was the nerve, and this was the muscle, and over here there was the drum. So, we are providing the stimulus at this particular point. Now, this impulse will travel along the nerve, will cross the neuromuscular junction, and will reach at the motor end plate. So, obviously, it will take some time, and that time, this is the point of the stimulus, that time we won't notice any contraction, because that now impulse is traveling, and ultimately when the muscle contracts, this is the contraction point. This is the contraction point. So, this duration from the application of the stimulus, the point of the stimulus, and whenever we notice the first upper flickering movement of the lever. So, it means the contraction has started. So, this duration is called as latent period, means it will take some time for us to notice the recording of the muscle contraction. Okay. So, the contraction has started. Because of the contraction, the muscle is contracting this way, this lever is moving upward. So, we will get upward deflection at this point. Now, the muscle has started relaxing, then it will come downward. Okay. So, and this is the baseline. So, our this marking pen of the lever, it should stop over here, but it's not stopping, it's going downward, then it's coming upward. Sometimes we get a slight 1 or 2 deflection over here. Why that is happening? That is happening because of the momentum of the lever. See, if anything is stationary, for it to move, like to start the movement of a stationary object, it will provide the resistance, right, that inertia. And once it becomes mobile, we want to make it stationary, obviously it will take some effort. So, because of that movement, that momentum is there, we will get one graph that is not because of the contraction of the muscle, and this graph is called as, this part is called as physiological curve. Okay, that is the another point. Okay, so now coming back to this latent period, what is the reason for the latent period? Like, what are the reasons why we are getting this particular latent period? So, what are the causes of the latent period? That is one question they can ask you. Number one, it is the time taken by, number one is time taken by the nerve impulse to conduct through the nerve, conduct along the nerve. So, we can say the time taken by the impulse, you can note it down, the time taken by the impulse to travel along the nerve. Okay. Now, what is the second reason for the latent period? Second reason is the neuromuscular transmission, or we can say the nerve impulse has reached at the neuromuscular junction. Now, that will make the this one neurotransmitter to get released. And what is the neurotransmitter over here? That is the acetylcholine. So, if you can recall, when the nerve impulse reaches at the end of the neuron, end of the nerve, at the neuromuscular junction, there will be the opening of the calcium channel. Calcium will enter inside the that at the synaptic area into the neuron, and that calcium along with the acetylcholine that is stored in the vesicles, there will occur the exocytosis. So, we can say that neuromuscular transmission time period, or the time taken by the neurotransmitter to get released at the neuromuscular junction, or we can say at the synapse. That is the second reason. The third one is, now that neurotransmitter will get attached to the motor end plate, receptor located at the motor end plate. Okay, and there will be time taken by that neurotransmitter to excite the receptor, to excite that, activate those receptor and excite the muscle. So, excitation contraction coupling, that impulse generated will travel along the muscle, will enter through the T tubule, ryanodine receptor will open up, calcium will enter into the cytoplasm from the sarcoplasmic reticulum, right, and then actin myosin sliding will occur. So, all these events, they will take their time. So, we can say the excitation contraction coupling, time taken by that process. Okay. Now, the fourth one we can say, it is when the muscle is contracting, say this is the muscle fiber, it is attached at both the ends through the tendon and the elastic, that elastic elements which are attached in series. So, when the muscle contracts, they will provide their resistance, right. This tendinous part of the muscle will provide the resistance. That is the fourth reason. The fifth one is, what was the reason for this physiological curve we were getting? The inertia of the lever. And what was the inertia? Because it was moving. So, a moving lever to become stationary, it will take some time. So, that is the reason for the physiological curve. Similarly, at the initial point, that this lever was in stationary condition. So, for it to make moving, right, that stationary inertia of the recording lever, that is also, it will also take some time. So, we can say there are the four reasons. One is the time taken by the impulse to travel along the nerve. Second is the events happening at the neuromuscular junction, release of the neurotransmitter, attachment of that neurotransmitter to the receptor, then generation of the end plate potential, right. The third one is movement of that action potential to travel along the muscle fiber through the T tubule, then making the ryanodine receptor to open up, that is located on the sarcoplasmic reticulum. So, the release of the calcium occurs into the cytoplasm, and that calcium will go and get attached, and the tropomyosin, that sliding will happen. So all these events that happening, we can say excitation, contraction, coupling, the events that is leading, ultimately leading to excitation, contraction, coupling, that will take some time. So time taken by those events. And the fourth one was the elastic component, the series elastic component, stretching of those, that will also involve some time. And the fifth one is inertia of stationary lever. So these are the 5 reasons for this latent period, right? Now at this point there is contraction starting, and the maximum point from here, if we draw the line, it will cut the baseline over here. So this period is called as contraction period, and when this curve comes down and crosses the baseline over here, this interval is called as relaxation period. So contraction period, relaxation period. So this contraction and relaxation period, the examiner might ask you, what is the normal duration of all these periods? The normal duration of the latent period is 0.01 second, and for the contraction period it is 0.04 second, and for the relaxation period it is 0.05. So it's easy to remember, the relaxation period is equal to contraction period plus latent period, and out of that latent period is of 0.01 second and contraction is 0.04. Now the question examiner might ask, can you calculate the relaxation period, contraction period, all these 3 periods in this graph? So your answer should be yes, we can calculate the duration. How will you calculate? Because you know by default in all these type of the graph, the speed, first of all it might be given over there, like as in this diagram it's written 640 millimeter per second. If it is not given, then by default we always take the speed of the drum is 640 millimeter per second. So if you know the speed of the drum, speed of the movement of the graph, then just measure this distance. Okay, measure this distance and calculate the period accordingly for the contraction, for the relaxation, as well as for the latent period. Okay, then what can be the other question? The other question can be like, what is the difference between the isotonic and the isometric contraction? That I won't go into detail, that you have to read through the theory part. Okay, like the isotonic, the muscle length might get shortened, but the tension will remain constant or the same. And isometric, the length is not affected. Iso, same length it stays. Okay, but the tension in the muscle might change. Okay, so that can be the other question. Now there can be one more question, like say you have prepared this nerve muscle preparation and you are stimulating the nerve. So where from the metabolites are coming, right? For any muscle to contract, it needs oxygen as well as the metabolite. For the oxygen, you can say it is drawing the oxygen from the environment, but the other metabolite, we always use the Ringer solution, and that Ringer solution we keep on putting on the muscle preparation drop by drop. Now what is the composition of the Ringer solution? The examiner might ask. The composition is, it has sodium chloride to maintain the isotonicity 0.6%. Okay, that is one component. The second is potassium chloride 0.14%. It helps in maintaining the membrane potential. This is for isotonicity, right? Isotonicity. That is a sodium chloride, potassium chloride. The third one is calcium chloride 0.012%. It maintains the muscle excitability. Okay, muscle excitability, as well as it increases the ATPase activity. Just remember, muscle for the muscle excitability. And the fourth one is, fourth and the last one, sodium bicarbonate, NaHCO3 in 0.02%. This is to provide the optimal pH. So sodium chloride for isotonicity, potassium chloride in maintaining the membrane potential, calcium chloride to maintain the muscle excitability, and NaHCO3 to provide the optimal pH. That is the composition of the ringer solution. So, we keep on pouring the ringer solution so that muscle keep on getting its metabolite. Okay, its metabolite. That is the other question they can ask. Then examiner can also ask, like, can you find out the tetanizing frequency from the simple muscle twitch? Like the tetanus part we will cover in the coming slides, but if you have been provided with simple muscle twitch, the examiner might ask, can you calculate the tetanizing frequency? It means like what should be the rate of stimulation, rate of providing the impulse per second or per millisecond, so that this muscle gets contracted, permanent contracted state, that is the tetanus. So, your answer should be yes, we can calculate the tetanizing frequency. So, the formula for to calculate the tetanizing frequency is 1 divided by contraction period duration in millisecond. So, we can calculate the contraction period because we know the speed, we can measure the distance, so that the contraction period in millisecond we will measure. So, 1 upon contraction period in millisecond, that will be equal to the tetanizing frequency. Okay. That is the other question. Now, sometime, that is like not the sometime, most of the times students might get confused, like this is the contraction and this is the relaxation in accordance with the action potential. No, this is the mechanical response, right? Say if the action potential is provided to a muscle, there is ionic things happening. That ionic events that's happening or electrical events that happening, that is called as the action potential, and whatever the mechanical events that's happening, that is the simple muscle twitch. So, this simple muscle twitch is mechanical events we are getting. Okay, to make it easier, let me take one picture. Say, where is that? Yes, this one. If we have a look at this point, this diagram, this blue line, it is the simple muscle twitch part, and it is in accordance with the stimulus, like we have provided the stimulus at this point, and this is, say if we draw a baseline over here, the movement of the graph starting from this baseline up to this point, this is the latent period, right? This is the contraction phase, this is the relaxation phase, that is the mechanical. This blue line depicts the mechanical events, but we have provided the stimulus at this point, and say this is the first dashed line is the application of the point of the stimulus. Okay, point of the stimulus, and this red line, it depicts the action potential generated in the muscle. So, this is the depolarization phase and this is the repolarization phase. So, depolarization and repolarization are the action potential or the electrical events, and this blue line, this simple muscle twitch, this is the mechanical event. So, when we say the refractory period, it will come in the coming slides, like the absolute refractory period and the relative refractory period. So, in this, the red line, the action potential, there are 3 dashed lines. The first one is point of the stimulus. The second dashed line, it covers the entire, in between this first and second dashed line, there is entire of the depolarization and a small part of the repolarization. This depicts the absolute refractory period, and from this second line to the third line, just at the end of the repolarization, this part, the number 2 depicted in this diagram, it shows this duration is relative refractory period. So, whatever we have read in the theory part, like if you provide the second stimulus in the absolute refractory period, we won't get any additive effect. So, this absolute refractory period and the relative refractive period, if we look at the blue line, it almost falls in the latent period phase. So, if we provide the stimulus in the contraction phase, that will lead to the summation of the impulses, right. So, this relative refractive period or the absolute refractive period, this is in accordance with the action potential, the electrical event. It is not with respect to this one is depolarization or this is repolarization. No, this is the mechanical event happening, right. Okay. Now, this is the second graph, and if you get this graph, you have to start with, like the examiner asked, comment on this graph. So, what will you say at the starting point? This is the graph showing the effect of temperature on the simple muscle twitch, right. Like this 26 degree centigrade, this 26 degree centigrade is the normal body temperature of frog, because we are performing this experiment on the frog nerve muscle preparation. So, 26 is normal body temperature. Sorry. So, we are performing the experiment to look for the what is the effect of the temperature, whether we are decreasing or increasing on the simple muscle twitch. So, what you are noticing at this point, if you look at this 16 degree centigrade means cold temperature. What is the effect of the cold temperature? For any effect to look, we will look for the effect on the latent period, the contraction period, the relaxation period, as well as height of the contraction amplitude. So, what is happening to the amplitude of the contraction? This is reduced, right, and this is the point of stimulus. The point of stimulus remains constant, like we are providing the stimulus at this particular point. So, this upper one, this graph at 38 degree means increased temperature. It is starting at the initial point, means the fastest out of these three, this is for the increased temperature, and the slowest to start is the one with the reduced temperature. So, we can say the latent period for the cold is from this point to this point. This latent period is increased if we reduce the temperature. The amplitude is reduced, or the height of this simple muscle twitch curve is reduced. And if we look for this one, say this point, this is the maximum height. So, if we draw the line this way, this is for the 26 and this is for the 38. So, from this point to this point, this is the latent period for the 16 degree one, and this is the contraction period, and the relaxation period is this one. So, if we compare all these three periods, the latent, the contraction and relaxation, it is maximum at the low temperature and minimum at the highest temperature. See, the latent period is this one, the shortest latent period, the shortest contraction period, the shortest relaxation period. So, what is the effect of temperature? If we increase the temperature, it will reduce the duration of all the three phases. It will reduce the duration of all the three phases, and if we reduce the temperature, it will increase the duration of all the three phases. The only thing which is getting reduced in reduced temperature is height of this curve, we can say it is reduced. Now, how will we perform this experiment? That can be the second question, like how will you increase or decrease the temperature? So, your answer should be by increasing or decreasing the temperature of the ringer solution. We are pouring the ringer solution, continuously pouring the ringer solution over that now muscle preparation, like on the muscle, so that it keeps on getting its own metabolite. So, we will reduce the temperature. The temperature of that ringer solution is 16 degree. So, obviously, that will reduce the temperature of the muscle. Now, there can be the question like first is what is the effect? Like there is increase in the duration of all the three phases in the at the cold temperature or reduced temperature. What can be the reason for that? right? Like what is the reason when there is uses of the cold ringer solution, or we are reducing the temperature, why the all the phases are increasing? So your answer should be because of the decrease in the temperature, there will be increase in the viscosity, like all these now this one muscle fiber, the tendon, though the elastic component, all of these things, the structure, these contacting part as well as the non-contactile part of the muscle, the viscosity will increase. So if there is increase in the viscosity due to the reduced temperature, it will provide more resistance. That is the one reason. Second is, some of the metabolic process will get reduced, because if we keep on decreasing the temperature, the activity of the enzyme will get affected, it will reduce. So metabolic activity, metabolic process will reduce. Okay. So these are the reasons for increase in the duration. It will take more time for the metabolic process to happen, right? And when we use the warm ringer solution or increase the temperature, it raises the temperature of the muscle, the contactile as well as the non-contactile. So obviously it will decrease the viscosity, that is one reason. Second is, if we increase the temperature within the optimal limit, over here is 38 degree centigrade, then the activity of the enzyme will increase. If we increase more than 38, say if we are using 45 degree centigrade, then what will happen? We won't get the graph more higher, no, it is the maximum 138. If we increase more temperature, then we won't get the effect. Why? Because all these events, whether we are using the 16 degree or the 38 degree, they are happening within the physiological limit. So once we cross the physiological limit, there will happen the denaturation of the protein, right? And what are the enzymes? All the enzymes are protein. So there will happen the denaturation of the enzyme. So enzyme activity won't happen, there won't be any metabolic activity. So increased temperature more than the physiological limit will denature the enzymes, so there won't be any effect. So the temperature is more than 45 degree, it will result in denaturation, and because enzyme will not be functional due to the shortage of the ATP, cross bridges will not separate and muscle will remain in a state of partial contraction, it won't relax. Okay. Now there might be one more question, like, is the effect of the temperature on the muscle contraction is not the violation of all or none law? Like either the muscle will contract or not contract at all. But over here, if you are increasing the temperature, it is contracting, it's increasing, the height is increasing, the duration is decreasing. Yes, the answer should be it is the violation of all or none law. Why? Because the all or none law, the first and foremost prerequisite is it is valid only if the environmental conditions are constant. And what are those environmental conditions? Temperature and pH. We are changing the temperature, it's not staying the constant, so obviously it is a violation of all or none law. So that is regarding the simple muscle twitch and effect of the temperature on simple muscle twitch.